Okay, so yes, so this is the tutorial on MBQC in the ZX calculus that was requested on our Google spreadsheet for requesting talks. And yes, so my plan is for this to be pretty interactive because it is supposed to be a tutorial. So please do ask questions if anything is unclear during the talk. And yeah, since this is the ZX meeting, I'm assuming that people are generally going to be familiar with at least the basic ideas of ZX, but I'm assuming that not everyone's going to be familiar with MBQC. Sorry, can you still see my slides, or has that done something weird to the area?
I can still see them.
Okay, right. Okay, so yeah, so this, I'm going to kind of start out by giving you the basics of measurement-based quantum computing, and then I'm going to spend the majority of the talk on flow conditions and applications with lots of examples, because I think, yeah, those things really sort of are a lot easier to understand by looking at examples. And then if time permits, at the very end, I'm going to talk a little bit about hypergraph MBQC, but that's not something that I know very much about myself, so we'll see whether we get to that. Right, okay, so we have two different models of quantum computation that are widely used. There's a few others that are kind of less well researched. But I assume you're probably all familiar with the circuit model of quantum computing, where we apply unitary gates kind of one after the other, or potentially some of them at the same time to different qubits. And we use measurements only at the very end of our computation to read out data. I guess potentially we can use measurements at an intermediate point and then have classical controlled gates later. But it turns out we don't need to do that. So we can always postpone all the measurements to the very end and only use those for reading out information. And the computation itself proceeds via these unitary gates. And the circuit-based model is kind of based on the idea of classical logic circuits. So that's something that corresponds reasonably well to things that we can also do in classical computation. But then the other model of quantum computation, the one-way model of measurement-based quantum computing, that's something that's very different that we can't do at all in classical computing. So in the one-way model, the basic idea is that we start by preparing some resource state. This is usually some form of graph state. I'm going to talk a little bit more about what graph states are on the next slide for those of you who aren't familiar with them. And then the majority of our computation proceeds via measurements. So I guess the only time we use unitary gates is going to be in the preparation of the graph state itself. And then potentially at the very end, we might have to do some unitary corrections via Pauli operations. But the bulk of the computation is done using measurements on the qubits in our resource state. And in the kind of standard version of MBQC, we do measurements we don't do arbitrary single qubit measurements, but we restrict ourselves to measurements in three so-called planes of the Bloch sphere. So either the XY plane, which in the ZX calculus is just a green dot, or the YZ plane, which in the ZX calculus is just a red dot with a phase, or the XZ plane, which is a red dot and a green pi/2 phase. So these are the kinds of measurements that we look at. And the reason for restricting ourselves to those planes is that, as we'll think about in a little bit, if we do a computation using measurements, the measurements aren't deterministic. So if we want our overall computation to be deterministic, we're going to need to do corrections. And if we restrict our measurements to being in these three planes, our corrections are always going to be Pauli operators. And that makes analyzing things a lot easier. Right, but first let's have a quick look at graph states. So graph states, as the name kind of implies, are quantum states that correspond to mathematical graphs. So a mathematical graph consists of a set of vertices and a set of edges connecting those vertices. And to prepare the corresponding quantum states, for each vertex, we prepare a qubit in the state plus. So in the ZX calculus, that's a green dot with an output. So actually throughout most of this talk, my kind of diagrams are going to go in circuit direction, so from left to right, but this one somehow goes from the bottom to the top. So apologies if that confuses anyone. Okay, so we have, for each qubit, we have a green dot with an output, so that's a qubit in the state plus. And then for each edge in the graph, we apply a control Z operation between the corresponding qubits. So for those of you who are less familiar with the sort of kind of modern notation in ZX calculus, so we've introduced this kind of new convention that if we have an edge with a Hadamard gate on it, that's just drawn as a dashed blue edge. So if I'm going to try the annotation thing, so this dashed blue edge is just the same as an edge with a Hadamard box. And I'm going to use that notation throughout this talk because it's going to just save on space and make things more straightforward. So why are these graph states interesting? Well, we have a kind of nice way of describing their entanglement structure. And we also know that they are stabilized by certain products of Pauli operators. So stabilized in this case means that they are eigenstates with eigenvalue 1. And so these operators of which they are eigenstates with eigenvalue 1 are products of Pauli matrices. So in this case, Pauli X and Pauli Z, or rather the sort of stabilizing set is generated by these products of just X's and Z's. It may contain products that include Y as well. But we can just read off from the description of the graph its set of stabilizers, or rather a generating set for the full set of stabilizers. And we pick one vertex in the graph, and for that vertex we apply an X gate, and then we also apply Z gates to all of its neighbors. So in this case, if we picked kind of the first vertex as our chosen one, then we'd apply a red pi to that vertex. Sorry, I'm just going to draw everything in blue because that's the color that's currently active. And then we apply green pies to all of its neighbors, which in this case is those two vertices. This one isn't a neighbor because there's no edge. And so this is now an operation that's a stabilizer of this graph state. So if we apply these three Paulis, actually the resulting quantum state is the same as the one we started with. And so in a way you can think of this as being able to take a red pi and sort of push it through the graph. And because there's Hadamard gates hidden in here, it turns into green pies, and those cancel out with those two pies over here. And that's why this is a stabilizer of our graph state. And this property of graph states is going to be very important later on, because we're going to use that to correct our errors. Right, so let's move on. So as I've already mentioned, when we're doing quantum computation using measurements, the measurements are probabilistic. So we're not guaranteed to always get the outcome that we want. But we want our computation overall to be deterministic. We don't want it to depend on the outcomes of individual measurements, or at least not too much. So there's always going to be, I guess, some amount of things that we can't correct using future measurements, because we'll have a kind of final measurement that we do, and if that doesn't come out right, then there's always going to be something else that we need to do. We might need to correct things by applying unitary operations. But for the bulk of the computation, we don't want to have to introduce any new unitaries. We just want to be able to correct things by modifying future measurements. And as I've mentioned, the idea is that we're going to push these errors, which always take the form of pi phases in the ZX calculus. We're going to push those through the graph state to qubits that we haven't measured yet. So yeah, I should mention, if we're doing this kind of measurement-based quantum computing, we're not going to do all the measurements at once. We generally do them in some specific order. And so if I'm measuring qubit 1 and some error occurs, then there are going to be other qubits that I haven't measured yet. And so I can still modify the measurement that I'm going to do on those other qubits. Of course, if there's a qubit that I've already measured, I can no longer modify what I do to that. So we need to make sure when we do this process of pushing pi phases through, that kind of all the pi phases end up on qubits that we haven't measured yet, and they don't have any effects on qubits that have already been measured. Oops, sorry. So of course, well, if we're talking about determinism, that means that, well, not all MBQC patterns are going to be deterministically implementable. So this pattern down here is one example of something that can't be implemented deterministically. So if you think about it, if I'm kind of doing the measurement on one of the qubits, and then sort of try and push the errors through to future qubits, that's fine. So because I haven't measured anything else yet. But then if I'm going to do, I'm going to have to basically correct the measurement on this first qubit by doing something to the later qubits, one or two of the qubits that I haven't measured yet. So, but when I measure the second qubit, at that point, I want to correct what happens to this qubit without affecting the qubit that I've already measured. And because both of our remaining output qubits here, those are the ones that we don't measure, they're outputs, because they're both adjacent to both of the input qubits, there's just no way that we are going to be able to correct the second measurement without affecting the first one. And so this is something that can't be implemented deterministically. And of course, if you're familiar with the ZX calculus, you'll see that this pattern here, this is actually something that's kind of equivalent to this sort of thing via the bialgebra rule. And so if you look at this, you can clearly see that this is something that has to kind of involve some measurement here, because we're going from 2 qubits to just 1 that transmits information further on. And so, yes, thinking from that perspective, we wouldn't expect this to be something that can be implemented deterministically, because there's always intrinsically some measurement in here. But many MBQC patterns can be implemented deterministically. And I'm going to spend the bulk of the talk now on talking about under which conditions we can deterministically implement things. So, and these conditions are known under the names of flow. There are all sorts of different versions of flow. And I'm going to kind of start with the simple one and then work our way forwards towards the more complicated ones. But before I go into the flow conditions, are there any questions about the kind of basic ideas of MBQC so far?
Quick question.
Yeah.
So when you're pushing all the Paulis to the end, you say that at the end you might have to implement some unitaries. Assuming that the rest of the pattern is deterministically implementable, is it possible to just always classically correct for these Paulis? Sorry, as in.
Well, it depends on kind of what you think of the end of your pattern as being like. So usually we kind of think, well, so if you measure all the qubits in your pattern, then I guess at the end, yeah, no, actually, I'm not entirely sure. So certainly, I mean, if you want to use your MBQC procedure to kind of prepare a certain quantum state, then at the end you won't be able to necessarily do classical corrections because it's the quantum state that's your desired product.
Yeah, sure.
If you're doing some computation where the end result is some classical data that you're reading out, then maybe, I'm not entirely sure. Maybe if the final measurement is like computational basis measurements or stabilizer measurements, then yes. Otherwise, probably not.
Right, that makes sense. Thanks. I was asking because in error correction you have this Pauli frame thing, which seems quite similar.
Right. Yeah, I mean, these things are all very closely connected. Yeah. Okay. So, any other questions? Right, and then let's move on to flow conditions. So first I'm going to introduce another concept that's going to be important throughout the rest of this talk, and that's the idea of a labeled open graph. So when we talk about the deterministic implementability of these MBQC patterns, usually we want them to be deterministically implementable independent of the measurement angles at individual qubits. And I guess sort of one of the motivations for that is that, well, if we're going to correct measurements, then we might need to change later angles. And so, yeah, we just don't want that to make a difference suddenly to whether we can implement things deterministically. So really, when we wonder about whether something can be implemented deterministically, usually what's relevant to us is kind of the underlying resource state, sort of its graph structure. which qubits in the resource state are input qubits and which ones are output qubits. So in the ZX diagram, input qubits have kind of an extra input edge to them, and output qubits are the ones that aren't measured. So they just have an output edge. And qubits could be both inputs and outputs at the same time. And what we also care about is what measurement plane a qubit is measured in. So that is something that is considered fixed. The angle itself is not fixed, but the plane is fixed. And in fact, yes, any corrections that we might apply, the Pauli corrections are never going to change what plane a measurement is in. So when we want to figure out whether something is deterministically implementable, we basically kind of need this information which is given over here. So I've here kind of drawn the input qubits as squares. I've drawn the output qubits as filled. And then for every non-output qubit, because the non-output qubits are the ones that are measured, I've specified the measurement plane. And the numbers here are just kind of labels that I've assigned to those qubits so that I can refer to them. So they could be arbitrary labels, just so we know what we're talking about. Okay, so that's what it means to be a labeled open graph. I should mention at this point that quite a lot of the kind of research in MBQC has focused on patterns where all the measurements are in the XY plane. So the reason for that is that XY plane measurements alone are already universal. So we can implement any quantum computation using just XY plane measurements. And of course, kind of by restricting things even further, reasoning about it is more straightforward. And so in the remainder of this talk, I'm often going to kind of talk about the XY plane version first, and then I'm going to look at the version that allows measurements in all three planes. Right. Okay, so if we do have one of those patterns which only has XY plane measurements, then there is a condition that is sufficient for determinism, which is called causal flow. And the idea behind causal flow is that for each qubit, we're going to pick one of its neighbors as kind of its assigned correction vertex. And so if something goes wrong on qubit A, then we've got the vertex f of A, and we're going to apply a correction to f of A that will cancel out the error that happened on qubit A. And so yeah, this map F is just the one that assigns a correction vertex to each measured vertex. And we also have alongside that a strict partial order. So that gives us some information about the order in which we need to measure the qubits. So if two qubits are incomparable in the partial order, then we can pick which one we measure first, or we could potentially even measure them at the same time. But if one qubit comes earlier than another in the partial order, then we have to measure that one first. And so the conditions that this partial order and the map F have to satisfy is that firstly, well, for each qubit, f of u is a neighbor. So the tilde here means that they're adjacent in the graph. For each qubit, its assigned correction vertex has to come later in the partial order, so that we're guaranteed that we haven't measured it yet and we can use it for corrections. And then for all neighbors of the correction vertex, those also have to come later in the partial order. Because when we apply a correction on the vertex V, that's going to affect all of its neighbors, not just u. Sorry, when we apply a correction on f of u, that's going to affect all the neighbors of f of u. And therefore, none of them can have been measured yet other than u, the one that we want to correct. So as an example, we've got this kind of very simple line graph down here. So if I kind of have an error on this first qubit, that would be a green pi. The only neighbor that we can choose to correct things is the second one. So we're going to apply a red pi to this one. Basically, this means just we kind of change the angle we're measuring this one in. So we're going to measure this at minus beta instead. And then if we push this red pi through the graph, it's going to cancel out this green pi over here. And it's also going to give us another green pi over there because it's going to move to all the neighbors of this vertex. But that's okay because we've done our job of cancelling out the error over here. And the qubit that we've affected, gamma, is one that we haven't measured yet. So we're allowed to change things on that because we can just adapt the measurement there. And so this one is going to then be measured at angle gamma plus pi. And then similarly, when we measure beta, if there's an error here, we're going to use gamma as its correction. And then the correction is going to affect this output vertex here as well, but that's fine. We're allowed to affect output vertices. And that would be a case where then if we wanted to keep using this state later on, we'd have to potentially apply an actual Pauli unitary to this qubit to correct this. Okay, so this is causal flow. So for each qubit, we choose a single qubit to correct any errors that might occur. And in this way, we can then deterministically implement a computation, because any error that occurs, we can correct using the assigned correction vertex. But there are cases where causal flow isn't enough. So there are patterns that we can implement deterministically, but which don't have causal flow. So one case would be if we have measurements that aren't in the XY plane, because causal flow is only defined if everything is in the XY plane. But even if all of our measurements are in the XY plane, there are still examples that do not have causal flow. And one example is the diagram that I'm showing down here. So we have 6 qubits. The first 3 are inputs and the last 3 are outputs. And as you can see, each output vertex is connected to more than one of the inputs. So I may be able to correct the first input qubit without affecting anything that's already been measured. In fact, I will definitely be able to do that because nothing's been measured yet. And for the second qubit, I can probably still find some way of correcting that, no matter which of these I measure first. So I could start with any of them. But when I measure the last qubit, the third one, there's not going to be any qubit that I can use to correct that without affecting qubits that have already been measured. And so this diagram here doesn't have causal flow. But as we'll see on a later slide, this is nevertheless a diagram that can be implemented deterministically. So causal flow isn't enough to always tell us when we can implement things. So instead, what we need is a broader condition, which is called generalized flow, or Gflow. So this definition is a bit of a mouthful, but don't worry too much. We're going to go through it in detail, and we'll look at lots of examples, which should make things clearer. So the idea is that rather than just using a single qubit to correct an error, we're going to pick an entire set of qubits. So we're allowed to pick as many qubits as we want. And again, we're going to have this partial order that kind of gives us some information, some constraints on what order we have to measure the qubits in. And we now have sort of generalizations of the conditions that we had for causal flow. So if some vertex W is in the correction set for some vertex V, then W has to come later in the partial order, because we're planning to modify its measurements, so we can't have measured it already. And also, if W is in the odd neighborhood of the correction set, and then either W has to be equaled, has to be the qubit we're currently trying to correct, or again, it has to be later in the partial order. And so the reason for that is that now that we have multiple qubits where we're applying corrections, they can potentially cancel out. So if I'm applying corrections to 2 qubits at the same time, and I have one qubit that's adjacent to both of them, then it's going to get pi's from both the other qubits, and those 2 pi's are just going to cancel each other out. So if something is in the even neighborhood of the correction set, we don't have to worry. That's not going to see any effect. But if things are in the odd neighborhood, that's when they do see a net effect. And so that's when we do have this condition on the partial order. And then these final 3 conditions, those are specific to different measurement planes. So because, as you may remember from a previous slide, we kind of, when our measurements go wrong, the error that we see depends on which plane we're measuring in. So if we're measuring in the XY plane, that was something where we have where our measurement is a green dot. And so if that goes wrong, we get a plus pi phase on that. So that corresponds to having a green pi. But if we're in the YZ plane, for example, then our measurement, again, would going wrong would imply that we see the angle alpha plus pi instead of just alpha. But of course, in this case, that means that our error is actually a red pi, not a green pi. And so that's why we have to treat the different measurement planes differently. So this condition 3 here is just the generalization of the condition we had in causal flow. So now rather than V needing to be adjacent to its single correction qubit, we now want V to be in the odd neighborhood of all its corrections. And in the case of the red, of a red measurement, a YZ plane measurement, we actually have this slightly weird condition of V being in its own correction set, but not in the odd neighborhood of the correction set. So that's just because the correction set really is just the set of qubits that are getting a red pi applied to them, and the odd neighborhood is the set of qubits that are getting a green pi applied to them. And in order to correct an error on a YZ measurement, we exactly have to apply a red pi to that to cancel out the error. So that's why V is in G of V, but not in the odd neighborhood. And then if our qubit is measured in the XZ plane, then we actually want both a green pi and a red pi to cancel out the error. So that's why V needs to be both in G of V and also in the odd neighborhood of G of V. Okay, so I'm thinking that's probably still quite a lot for those of you who haven't come across this concept of generalized flow before. So let's now look at some examples of how this works. The first example is the kind of slightly simpler one where we're just looking at XY plane measurements. So we can ignore the sort of conditions 4 and 5 of the Gflow because nothing is measured in those planes. And now if you look at this diagram, that is just the diagram we saw a couple of slides ago as an example of something that doesn't have causal flow, but where I said it is deterministically implementable anyway. And we'll now see why that is by specifying a Gflow for this example. Okay. So for the rest of the talk, I'm kind of generally writing my Gflows in kind of as a table down here. So I'm kind of the top row is going to have all the non-output vertices. So all the vertices that are measured. And then underneath, I'm going to write the correction set for each of those vertices. And then to make things simple, I'm also specifying the odd neighborhood of each correction set. And then over here, I've got another graph, which has the same vertices as our original graph. But in this graph, the edges kind of show us the conditions on the partial order. So kind of an arrow from 1 to 2 means that 2 has to come later in the partial order than 1 does. I'm not drawing like every single condition that is part of the partial order. So the actual full partial order is going to be the transitive closure of the arrows in this graph. But hopefully this is going to kind of give you an idea of what's going on here. So in this case, we're going to start by measuring vertex 1 first. So this is the kind of bottom element in our partial order. And its correction set is the vertex 2. And a correction on 2 is going to affect vertex 1 and vertex 3. So vertex 1 is the one we want to affect to correct it. Vertex 3 is also affected, but that's fine because we haven't measured it yet. And that's why we have an edge here between 1 and 3 to say that we definitely have to measure 3 after 1. Okay, and then next we could now choose, we could either measure 3 first or 5 first. In this case, I've gone for 3. So when we measure 3, our correction vertex is going to be vertex 4. And the odd neighborhood of 4 is going to be vertices 3 and 5. So again, 3 is the one we want to correct. And 5 is going to be affected as well, but that's okay because 5 hasn't been measured yet. And again, that means that 5 has to come after 3 in our partial order. And then finally, we're going to measure vertex 5. And in this case, our correction set is both vertex 2 and vertex 6. So this is where our flow really becomes a Gflow. So as I explained earlier, kind of we can't find correction sets where each correction set only has a single element, then we'd have a causal flow. That's not possible here, but yeah, so this set really makes it a Gflow. And you can see here now, if we correct on both 6 and 2, then the corrections from 2 are going to cancel out the effects from 6 on vertices 1 and 3. So the odd neighborhood of this correction set is really only vertex 5, which is the one we want to correct. And we're not going to see any effects on vertices 1 and 3, which are already measured. And then yes, we're potentially going to have to apply Pauli unitaries to our outputs in order to do those corrections. But that's okay, we're allowed to do that. Right, does that make sense so far? No complaints.
Yep, fine so far.
Okay, so now let's kind of level up slightly and look at the next stage of Gflow with multiple measurement planes. So we've still got a lot of qubits that are measured in the XY plane, but we've now also got this qubit over here, which is measured in the YZ plane. And so again, I've left out the condition for the XZ plane because we're not using that in this pattern. And so I'm adding here to the Gflow table just the measurement planes, so we can keep track of those. And again, we've got our correction sets here. I guess kind of looking at the corrections for the XY measurement vertices isn't going to be that interesting because we've already seen that. But when we look at vertex 4, that's the one that's measured in the YZ plane. So our condition up here says that we want the vertex 4 to be in G of V, and we don't want it to be in the odd neighborhood of that correction set. So 4 is contained in the correction set here. And then of course, if our correction set was only vertex 4, we'd then affect vertices 1 and 5. And those turn out to be ones that, well, I guess we potentially, depending on what order we're doing things in, maybe we don't mind affecting those. But also we could, for example, add 2 and 6 to our 2 and 6 to the correction set as well. And in that case, we no longer affect 1 and 5. The effects are only on vertices 3 and 7, which are outputs, and effects on outputs are always okay. And so this choice of Gflow is going to give us this sort of set of kind of constraints on the partial order. Yeah, so actually with this choice, we can kind of choose what order we're measuring 1, 4, and 5 in, because they're all incomparable. But we definitely have to measure all 3 of them before we then go on to measure 2 and 6. Because yeah, 2 and 6 are the ones that correct for those ones. And so note it's actually okay to have vertices showing up in correction sets for multiple different qubits, because the kind of we actually want to achieve different effects in different places. And so here in the case of vertex 1, we actually kind of the thing we're trying to achieve is to get the odd neighborhood, to get 1 to be in the odd neighborhood. But over here, what we're trying to achieve is just kind of make sure that we have more flexibility in terms of what order we measure these things in. And so that's why vertex 2 shows up again over here. But actually it just cancels out the effect from vertex 4. Yeah, does that make sense?
So far, so good.
Okay, thank you. Right. So Gflows are not generally unique. So for any given labeled open graph, we might actually be able to find multiple different Gflows. So kind of how do we, like the kind of next thing to look at is which Gflows are particularly nice or particularly useful. And there's this concept which is called a maximally delayed Gflow. And that's going to turn out to be particularly nice. And also maximally delayed Gflow is useful if you want to kind of, if you're given some pattern, you want to figure out whether it has a Gflow. So it turns out there's kind of a straightforward algorithm that always spits out a maximally delayed Gflow. But what does this idea of delay for a Gflow mean? So basically what we're doing is we're defining a sort of, again, a sort of partial order, but now the partial order isn't on the vertices. The partial order is between different Gflows for the same pattern, for the same labeled open graph. And the way that we're defining this partial order is by splitting our vertices into layers according to the partial order of the Gflow. So my example here is again going to be the one that has generalized flow but not causal flow. And the first example is the Gflow that we saw a couple of slides back. And so here, if we want to split things into layers, we always start from the back. So we look at our first layer is going to be all the maximal elements according to the partial order. So over here, well, maximal elements means the vertices that only have arrows going in. And so that's these three. In fact, the sort of first layer, or sort of the top layer of any Gflow is always going to be the output vertices. You can prove that. Okay, so our first layer is these outputs. And then we ignore those. And we now look at, well, what are now the maximal elements in our Gflow partial order? So now the next vertex that we have that only has arrows going in is just the single vertex 5 over here. So that's going to be our next layer. So I guess this one's layer 1, this one, sorry, layer 0, layer 1. And then we've got another layer over here, which is layer 2. And then finally, we've got layer 3. So this Gflow has 4 layers. And yeah, the top layer is always going to be just the outputs, and then the others may depend on the Gflow. And yeah, in fact, if we look at the second Gflow down here, which is a Gflow for the same graph, but it looks slightly different. So you can see we have different vertices in the correction sets for 1 and 3. Then what we have over here is again our 0th layer in the partial order is the same one. But now we only have one other layer which contains all the remaining vertices. And so that means when we kind of go through the layers, starting from the 0th one and then looking at the next one, we see the vertices earlier in this Gflow than we do in that Gflow. And that means that this Gflow down here is more delayed than the one up there. So more delayed means that we want to see vertices earlier. Either by, I guess, yeah, so in this case it's kind of obvious because we have different numbers of layers in total, but we could also potentially have the same number of layers. It's just that kind of, yeah, some of the vertices appear in different layers in different Gflows. Right, so in this case, the Gflow down here is more delayed than the one up here. And in fact, you can prove that this one is a maximally delayed Gflow. So there's no Gflow on this same labeled open graph, which is more delayed. And sort of one argument that you can make to prove that is to kind of say that any layer can have at most as many elements as the layer, as kind of there are outputs, because otherwise how would we be able to correct everything? And so, yeah, there's just kind of no way that we can compress these things even more so that we see vertices later on. Right. Yeah, so these, we can define, to summarize, we can define this order on Gflows, where we say some Gflow is more delayed than another, just according to the partial order on the vertices. And a more delayed Gflow basically means we have fewer constraints on the measurements, or at least we can kind of delay measurements more. And that means, yeah, additionally, it means kind of when we implement the computation, potentially we can do it quicker, because things that are in the same layer are things that we can do the measurements at the same time and then do the corrections at the same time. Okay. So that's still not quite enough. So there's still sort of other interesting variants on Gflow that we can look at and define. So another really useful version of Gflow is called focus Gflow. And yeah, I'm not quite sure off the top of my head. I was trying to figure this out and didn't have quite enough time to look it up. I think focus Gflow may always be maximally delayed, but I may be wrong about that. Anyway, so a focus Gflow which was originally defined just for Gflows with XY plane measurements, is a Gflow where kind of when we're correcting an error on some vertex V, our corrections are only going to affect via the odd neighborhood that vertex V itself and output vertices. So the only non-output vertex that is affected is V. So that kind of means that all of our constraints in terms of the partial order only come from vertices being in the correction sets for another vertex. We don't have any extra constraints by things appearing in the odd neighborhood of the correction set. And so that means that, in fact, we don't even need to explicitly specify the partial order, because the partial order is just given by sort of the relationship of a vertex appears in the correction set of another. And this is particularly nice. So it has the following properties. If we have some graph where all the measurements are in the XY plane, and this graph has a Gflow, then we know it must also have a focused Gflow. So kind of, yeah, whenever there is a Gflow, we can also find this kind of more specific version of focused Gflow. And in fact, if our graph has equal numbers of inputs and outputs, so that means it can represent a unitary operator, and it has Gflow, then this focused Gflow is in fact unique. So that's a nice property, because I said in general, Gflow is not unique. And then finally, I'm not going to go into any detail on this, but if we have an operation, a labeled open graph with equal numbers of inputs and outputs, and it has a focused Gflow, then this focused Gflow is reversible. So that means if we kind of swap what are the inputs and what are the outputs, we can immediately specify a Gflow for this new labeled open graph by kind of changing the relationship between so if a vertex was originally in the correction set of another vertex, then the other vertex is now going to appear in the correction set of the original one. So we're kind of, yeah, basically just flipping the partial order around. And that will again give us a focused Gflow. So that's, yeah, a really nice property. Right, so again, this is my example heavy talk, so let's look at an example of what this means. So this time we have a slightly different diagram up here. And kind of the sort of, yeah, maybe like naive, most straightforward Gflow that we could write down for this thing is actually a causal flow, where each correction set only has a single element. And it's going to have this partial order over here. So we have kind of these sideways arrows where when we're correcting our vertex 1, we're actually going to affect the vertex 5 and vertex 3 as well. And similarly, when we're correcting vertex 4, that's going to have side effects on 2 and 6. So because of that, this Gflow is not focused. So I guess we don't care about the 3 and the 6 because those are outputs, but we do care about the fact that this correction affects vertex 5, which is not an output, and this correction affects vertex 2, which is also not an output. So we can instead write down a focused Gflow for the same graph. So this has different correction sets. And now all the odd neighborhoods of our correction sets consist only of the vertex we're trying to correct, and then potentially some output vertices. And for outputs, we don't care about effects on those. And so this means that we kind of now have fewer constraints here, or like slightly looser constraints between in the partial order. Right, so there's kind of an algorithm to find a focused Gflow if you are given an arbitrary Gflow on a labeled open graph. I'm not going to go through this in detail, but basically the idea is that sort of if you have some vertex in your odd neighborhood that you don't want to affect, then you can cancel out the effect on that vertex by basically in the same way that you would normally cancel out an error. So here we're affecting vertex 2, which we want to avoid, but we have a correction set for vertex 2. And so we just add that correction set to the correction set for vertex 4 here to cancel out the effect on 2. And this works out because well, since 2 is affected by the correction on 4, that means 2 must come later in the partial order than 4. And so vertex 3, which is the correction for 2, must come even later than 2. And so it must also come later than 4. And so we're allowed to add it to the correction set over here. And in this way, we can always get from a non-focused Gflow to a focused Gflow. Right. But this definition so far was again just for measurements in the XY plane. We can extend this definition to the case of multiple measurement planes. So it's not like a priori obvious what is sort of a good way of extending this definition. So in fact, there was a paper by Miriam Backens where they kind of thought about restricting side effects of corrections to be only a single type of Pauli operator. So that gives you basically sort of 3 different versions of focused Gflow. One where correcting a vertex can only give you side effects that are Pauli X, one where all the side effects have to be Pauli Y, and one where all the side effects have to be Pauli Z. So by side effects, I mean effects on vertices other than outputs and the vertex you're trying to correct. But in work that I did with Hector and Giovanni and Leo and John, we came up with a different definition that extends focused Gflow to multiple measurement planes, which turned out to be more useful for the case that we wanted to use this focused Gflow for. And that's something that I'm going to move on in a moment, which is the idea of extracting circuits from measurement patterns or ZX diagrams. And so for that, it turned out the most useful definition turned out to be the following. So we don't kind of restrict what corrections we allow across the entire diagram, but we restrict whether vertices are allowed to appear in correction sets or in odd neighborhoods of correction sets, depending on what measurement plane that vertex is measured in. So again, this is something that generalizes the original notion of focused Gflow. So if everything is just measured in the XY plane, then this definition, or yeah, I've phrased it as a proposition for some reason because that's the way it was in our paper. So if everything's measured in the XY plane, then this just reduces to the previous definition. But if we allow multiple planes, then that's where this new clause becomes interesting. So if we have a vertex in the correction set of some other vertex V, which is not an output, then either W has to be V, or it has to be measured in the XY plane. So vertices that appear in correction sets can only be either outputs, or the vertex we're trying to correct, or arbitrary vertices that are measured in the XY plane. And then similarly, if we're looking at the odd neighborhood of a correction set, then the vertices that are allowed to appear in that are either outputs, or the vertex we're trying to correct, or arbitrary vertices that are not measured in the XY plane. So it's kind of, yeah, we have a nice symmetry here because a vertex will only appear in the odd neighborhood of its own correction set if it's measured in the XY plane. And similarly, a vertex will only appear in its own correction set if it's not measured in the XY plane. So it's kind of an interesting symmetry here. But yes, so that turned out to be the definition that we needed to be able to extract circuits from measurement patterns and ZX diagrams. I had, no, I don't have an example of this. I'm moving straight on to circuit extraction, which is good because time is short. So yeah, so why do we care about these flow conditions? Well, firstly, kind of, I guess from the MBQC perspective, we want to know whether our measurement-based quantum computations can be implemented deterministically. But from the ZX perspective, we're interested in them because they allow us to take ZX diagrams and transform them into quantum circuits. So it's not a priori obvious if you're given some ZX diagram, whether you can transform it into a quantum circuit. And even if you're kind of guaranteed that the diagram represents a unitary, which is obviously a prerequisite for it to be able to be transformed into a circuit, even then you might not actually know kind of how to go about turning it into a circuit. And so this is again the example that shows that in the MBQC case, there are diagrams that don't have causal flow, but are deterministically implementable. So we've seen a Gflow for this. We know that it can be implemented deterministically. And Duncan, Kissinger, Perdrix, and van der Wetering showed that if you have one of these diagrams and you have a Gflow for it, that allows you to transform this ZX diagram into a circuit-like one. So I guess this starting diagram we could kind of call MBQC-like, because yeah, it kind of consists of this graph state with measurements on some of the vertices. And our goal is to have something that looks like a circuit. And so this is something that we can do as follows. First, we'll merge the measurement effects into the vertices. This is just kind of tidying the diagram up a bit. And now it turns out that if we apply a controlled NOT gate to one of those, to the outputs, and then kind of apply some diagram transformations, that's going to allow us to toggle certain edges between these two layers of vertices here. So this layer of vertices, the kind of topmost one, is generally called the frontier. And this is kind of the unextracted part of the diagram. And this over here is called the extracted part of the diagram. And so the extracted part has to be a circuit-like. The unextracted part is MBQC-like. And then in between here, we just have Hadamard edges that connect the frontier to the unextracted part. So we've added two controlled NOT gates here, and they cancel each other out, so this doesn't change the meaning of the diagram overall. And we can now kind of do ZX transformations here, which I'm stepping through quite quickly because yeah, I'm running quite short on time. But basically these give us extra Hadamard edges over here. And if we have two Hadamard edges connecting the same pair of green vertices, the two Hadamard edges cancel out. That's a version of the Hopf law. So they go away. And now we only have a single edge left here that's connecting this frontier vertex to something in the unextracted part of the diagram. So we can kind of pull out the vertex from the unextracted diagram. And sorry, I'm somehow missing an edge over here. The Hadamard edge has now turned back into a Hadamard gate. And of course now this does not look circuit-like yet. We have this weird node here which has a phase but also has multiple connections. So we can extract a phase gate here and a control Z gate. And then again, we now, in this case, luckily happen to have another vertex here which only has a single edge connecting it to the unextracted part. So we can do the same thing again, pulling out a vertex from the unextracted part. The Hadamard edge turns into just a Hadamard gate. And then again, we pull out the phase gate and the control Z and continue like that. And now we've managed to turn our MBQC-like diagram into a circuit-like diagram where we've only got control NOT gates and control Z gates and I guess swap gates over here, and then some single qubit gates. So it's immediately obvious how to implement this as a circuit. Right, but this was kind of the original approach to circuit extraction, and that only worked if all the measurements are in the XY plane. So we've since managed to extend this work so that it also works for measurement-based patterns with measurements in arbitrary planes. And so just as an example, I'm going to go through the case of this diagram, which has one YZ plane measurement. So this kind of structure is really what's known as a phase gadget. So this gives us effectively some kind of controlled phase gate on different qubits. But yeah, it wasn't necessarily obvious a priori how we would go about extracting that. So firstly, when we want to extract a circuit here, well, we can start with these vertices that only have XY plane measurements, so we know how to do that. We can pull out things from the unextracted part in the same way as we did before. And so this point is really where things get interesting, because now the only thing that we have in the unextracted part of the diagram is this phase gadget vertex, which is measured in the YZ plane. And so what we were able to show is that if we apply a fixed point operation, a pivot, to the phase gadget vertex and one of its neighbors in the frontier, that is something that actually preserves Gflow in the unextracted part of the diagram. So in this case, this is kind of trivial because the unextracted part at this point no longer contains anything. So I didn't choose my example very well. But yeah, the idea is that we can do this operation which changes our diagram while preserving the interpretation of the diagram, and also preserving the fact that the unextracted part of the diagram has Gflow. And so I'm not really talking much about Gflow in these extraction examples, but really kind of a lot of the arguments for why this algorithm, the circuit extraction algorithm, works rely on the fact that the unextracted part of the diagram has a Gflow. And therefore we need to care about the fact that sort of anything we do doesn't break that Gflow. So what we're doing here is, because currently we don't have any more vertices here, we're just going to introduce a new one. So if there was more stuff in that diagram, we wouldn't have to do this. This is kind of just, to make things look nicer. And now we're going to apply a pivot across these two vertices. So that gives us Hadamard gates on the outgoing wires, and it also kind of changes some of the edges in the diagram. But now, of course, we have a Hadamard gate here next to the YZ plane measurement. And so that means this actually turns into an XY plane measurement. And yeah, there was this kind of, this Hadamard edge here, which I've extracted as a Control Z gate. And now we are back to the previous case of a diagram where all the measurements are in the XY plane. So this is something we already know how to extract. So we can just kind of continue in that vein. And that gives us all the, a circuit that we can extract. This is, as far as I know, it is both the kind of most general circuit extraction algorithm for MBQC patterns that doesn't use ancillars. So if you're applying this algorithm to a diagram with equal numbers of inputs and outputs, you're always going to get an ancillar-free circuit. And many other approaches to getting circuits from MBQC patterns do involve ancillars in some way. And also this circuit extraction algorithm is the most general algorithm we have for extracting circuits from ZX diagrams in general. So of course it's not going to work for all ZX diagrams because a precondition is that the ZX diagram be MBQC-like and that it have a Gflow. But again, sort of circuit extraction for arbitrary ZX diagrams is not something that's solved. And so this is kind of the most general algorithm that we have. And that's kind of one of the big reasons why we care about Gflow and MBQC in ZX. So it's kind of a, basically win-win situation where we learn more stuff about MBQC, but we also learn more stuff about ZX. Right, so now I'm already slightly over time, so I don't think I'm going to have time to go through the hypergraph MBQC stuff. I'm just going to kind of show you a list of references, which hopefully contains all the things that I've kind of mentioned during this talk on the slides. I'm not claiming in any way that this is kind of a complete version of all the important papers about ZX and MBQC. But in fact, I really should have included the kind of original paper about doing like circuit extraction from MBQC patterns in ZX calculus by Duncan and Perdrix. But yeah, so this is at least the ones that I've directly mentioned in my talk. Thanks for your attention, and are there any other questions?
First, let's thank Miriam for agreeing to give this tutorial. Nice. Any questions?
When you're doing the pivots in the extraction method for different planes, the title of the title that it was up at the top was circuit extraction for phase gadgets.
Yeah.
Does this mean that an equivalent thing would be to spot that this this thing that you're trying to extract is a gadget in a particular basis? So maybe I'm not explaining this what I'm thinking very well, but the thing that you get out afterwards is from this this measurement in a different basis here is I think a ZZ gate with some angle. Yep, there. So is it equivalent to just to algorithmically spot and look for these things rather than doing manually doing pivots and I assume whatever other graph preserving stuff?
I guess you could potentially try and manually spot these. It just kind of, in this way, it sort of integrates neatly into the circuit extraction algorithm for the XY plane measurements. So yeah, I mean, I think sort of with the kind of multi-plane focused Gflow that we defined, actually the kind of phase gadget vertices, so the ones that are measured in the XZ or YZ planes, never appear in correction sets, and therefore you can actually drop all of those vertices from the diagram and still have something that has Gflow. So yeah, so I think in theory you could kind of treat them separately. But yeah, using those pivots just kind of makes for like a neat overall algorithm.
Yeah, thank you.
Any other questions? Okay, I think in that case I'm gonna stop the recording.
Yeah, then let's thank Miriam again for giving us a talk.